Okay, welcome to the second review of Chemistry 2, Unit 3. Today we're going to be covering Ka, Kb, and Kw, essentially going over how to calculate Ka from pH, how to calculate pH from Ka, and also the same for Kb, and also review the relationship between Ka, Kb, and Kw. So, first we're going to start with how to calculate Ka from pH. We're going to look at the equation HCOOH plus water gives us HCOO net all to the minus 1 plus H3O plus. So to write out the expression for Ka, we're going to do the same thing where we take the products over the reactants. We're only going to include the HCOOH because we know that H2O is a pure liquid, which we just don't include those. To calculate Ka, we need the equilibrium concentration of all species. We need to find the concentration of H3O plus, which is the same as HCOO minus from the pH. We can tell that this is the case by looking at the equation that the concentration of H3O plus is the same as HCOO negative because we look at the stoichiometry. We can go back to this equation up here. We can see that for 1 mole of HCOO negative, there is 1 mole of H3O positive. So we can essentially deduce that both of these are going to be the same value. So they're both going to be X. Now for an example problem, we're going to do the pH of a 0.1 molar solution of formic acid, which is going to be our HCOOH, at 25 degrees Celsius is 2.83. Calculate Ka for formic acid at this temperature. What we're going to do is we're going to write an ice chart. We're going to write out our reactant and our products. Since we're starting with a solution of 0.1 molar, we're going to put that in our initial box for formic acid. Since it's the beginning of the solution, we're not going to have any H3O plus, and we're also not going to have any HCOO minus. Next, we can deduce the change boxes by looking at the stoichiometry. Up here, for 1 mole of HCOOH, we lose to gain 1 mole of HCOO negative and 1 mole of H3O plus. So we write that here. Next, at equilibrium, we combine these two boxes. For formic acid, we get 0.10 minus X. And for both the reactants, we get just X. So we can go back to this, and we can confirm that we can find the H3O plus and HCOO minus are the same. So we can see that H3O plus is equal to 10 to the negative 2.38. We get that because it gives us the pH. So what it's asking is calculate the Ka for formic acid at this temperature. Remember that Ka is equal to the expression, H3O plus times HCOO minus over HCOOH. This is what our Ka is going to equal. Now, we know that the pH is 2.38. So we can use the pH, similar like we did in the last review, to calculate the concentration of H3O+. So we can see that by doing so, we can take 10 and put it to the negative of the pH to get the concentration 4.17 times 10 to the negative 3. That is our concentration for H3O+. And by using the ice chart, we can also deduce that this is also X. So we calculate those numbers into the expression, and that becomes 417 times 10 to negative 3. Since we have two x's multiplying to each other, we're going to square this. And then we're going to take 0.10 minus x. Now, you're going to notice that this is going to be a quadratic. We're going to try and avoid quadratic equations as much as possible. But we know that x is going to be a very small number. So in most of these equations, you can just exclude the x. So we take 4.17 times 10 to the negative 3 squared divided by 0.1. If we go ahead and input that into the calculator, 4.17 times 10 to the negative 3 squared gives us 1.73889 times 10 to the negative 5th. Now we divide that number by 0.1 to give us 1.73. And actually, we're going to make that a 4 times 10 to the negative 4. Okay, so that is how you calculate Ka from pH. Okay. Now we're going to look on how to calculate pH from Ka. The problem says calculate the pH of a 0.3 molar solution of acetic acid at 25 degrees Celsius. The Ka for acetic acid at 25 degrees Celsius is 1.8 times 10 to the negative 5th. Is acetic acid stronger or weaker than formic acid, which we determined that the Ka was roughly 1.8 times 10 to the negative 4th. To solve this, we're going to follow these steps, and you're going to follow these steps for almost every single one of these problems. So first, you're going to take and find the equilibrium constant expression. To do so, we need to take the equation for acetic acid. So we do C2H3O 2H plus H2O gives us, and this is going to be your acid. So remember that your acid is going to work as a protein donor. So that is going to turn into C2H3O2 minus. And then this, the water is acting as our base. So it's going to be working as a proton acceptor. So it's going to turn into H3O plus. Okay. So now that we have the equation, we can write the equilibrium constant expression. Again, remember that to write the equilibrium constant expression, you're going to take the concentration of your products over the concentration of your reactant, with water excluded, of course. Okay, so that is going to be our equilibrium constant expression. I'm going to also extend this text mode, so we have a little bit more space to work. Okay, drag back over here. Now we have to create an ice table like the one above. So first thing we do is write out ice, I, C, E, the I standing for initial, the C standing for change, and the E standing for equilibrium. Next, we're going to write our concentrations. So we have C2H3O2H, and then we have C2H3O2 minus, and then also the concentration of H3O plus. So going back to our original problem, we can find that there is 0.3 molar of acetic acid initially. So right here we go, we put 0.3 molar. Okay. And we can find that there are no initial values for either of the products. So we're just going to put 0 and 0. Now, to find the change, we have to look at the stoichiometry. We can look at the stoichiometry in the equation that we wrote. For 1 mole of acetic acid, I believe, yes, acetic acid, we get 1 mole of C2H3O2 minus and 1 mole of H3O plus. So for change, we put minus 1 mole, plus 1 mole, plus 1 mole. And then we combine these to find our equilibrium. So it's going to be 0.3 minus x, x, x. This is our completed ice chart. The second step, or the third step, is going to be equal to x replaced expression to the Ka value. So we know that Ka is equal to this expression. So what we're going to do is replace our values, 0.30 minus x, x, and x, into this expression. I'm going to do that right here. So we know that x is a concentration for C2H3O2 minus, and that x is also the concentration that we know so far for H3O plus. However, for the concentration of C2H3O2H, or acetic acid, we find that it is 0.3 minus x. So we're going to go ahead and write that down as well. Okay. Now, we're going to equal the x replaced expression to the Ka value. We know that the Ka value is going to be 1.8 times 10 to the negative 4th. Now, all we have to do is, like above, solve for x. So what we're going to do is we're going to come down here and we're going to rewrite it. So we have two x's multiplying by each other. So it's going to be x squared. Then we have 0.3 minus x is equal to 1.8 times 10 to the negative 4th. Okay. Now, just like above, we're going to exclude this x to avoid doing quadratics. And we're going to multiply 1.8 times 10 to the negative 4th by 0.3. And that is going to give us That gives us 5.4 times 10 to the negative fifth equal to x squared. To find x, all we have to do is take the square root of this number. So we find that x is equal to 7.334 times, and I'm just writing this here because we're losing space, times 10 to the negative 3. Now to find the pH, we have to take the concentration of H3O plus, which we know is now 7.34 times 10 to the negative 3. So we take the concentration, and we know that the concentration of H3O plus is equal, so hold on, so we know that pH, is equal to the negative log of the H3O plus concentration. So all we're going to do is input this number right here. So we do negative log, and then we put our answer in. We find that the pH of this certain problem is going to equal 2.13. Okay. So going back to a question, we say, is acetic acid stronger or weaker than formic acid? The Ka value. So we know that the pH of formic acid is 2.38, and then that the pH of acetic acid is 2.13. We know that acetic acid is going to be the stronger acid because it has a lower pH. Okay, now we can look at calculating pH of basic solutions. Essentially, we're going to do the same thing of this problem, but instead of finding pH based on the x value of H3O plus, we're going to find the pOH value based on the value of OH minus. So we're going to follow the same problem. So we know that the pH, what is the pH of a 0.5 molar solution of NH3? So first thing we're going to do is we're going to write the equation for NH3. NH3 plus H2O gives us, we know that we're looking for, we know that this acts as a base, so it's going to work as a electron, oh my gosh, sorry, proton acceptor. So we're now going to have NH4 plus, and then water is acting as our acid, so it's going to be losing a proton, giving us OH negative. Next, we're going to write our expression for Kb. Remember that it's products over our reactant, excluding water. Okay. So now that we know that Kb equals this expression, we can go ahead and write our ice chart. I'm going to also extend this. I guess I should extend it. So going ahead and writing our ice chart, I, C, E. At the top, we have NH3, then NH4 plus, and then OH negative. By going back and looking at the problem, we can find that we already have 0.15 molar solution of NH3 in the solution. So we're just going to put 0.15 molar for our base. We have 0 of NH4 plus and 0 of OH negative. By looking at the stoichiometry, you can tell that it's 1 to 1. For 1 molar of NH3, you get 1 molar of NH4 plus and 1 molar of OH negative. So our ice chart is going to be minus X plus X plus X. And by combining both, we can find equilibrium. So it's going to be 0.15 minus X, X, X. Now that we find these equilibrium values, we can input these values back into our KB expression. So now it's going to be, remember, X times X. It's going to give us X squared. And then our NH3 concentration is going to be 0.15 minus X. But remember that we're excluding the X to avoid quadratic problems. So it's going to be 0.15. We also know that the KB is equal to 1.8 times 10 to the negative fifth. So we're going to go ahead and equal. Okay. Now we're going to go ahead and solve for X. I'm just going to do that really quickly. So we're going to take 1.8 times 10 to the negative fifth. And we're going to multiply that by 0.15, which gives us 2.7 times 10 to the negative 6. And we're just going to square root that number to find X. And we're left with what will be 1.64 times 10 to the negative 3. Those are our this is our concentration for our NH4 plus and OH negative. Now, remember that we want to find the pH, but we have no H3O plus, which is used to find pH. So how can we find pH if what we have is OH negative? First, we're going to find the POH. POH is found very similarly to this equation right here. So we're going to write, come down here, or already here. POH is equal to the negative log of the concentration of OH minus. So by just replacing these numbers, we're going to find negative log of 1.64 times 10 to the negative third gives us a POH of 2.78, roughly. This is our POH number, but what we're looking for is pH. Now, remember that POH plus pH is always going to equal 14. So what we need to do is subtract 2.78 from 14 to get our pH. So by doing that, I'm going to go ahead and write it. And we're going to find that our pH is equal to 12 point, sorry, 11.22. Next, we're going to look at calculating percent ionization. This is a way to check the work that we did above. So percent ionization is equal to the amount ionized divided by total in solution times 100. So say we have 4.17 times 10 to the third. That would be one of our concentrations. So X. And you divide that by the total in solution, which is going to be our initial. So we take our concentration, X, divided by our initial in solution, and multiply that by 100 to get a number. We use this to check work, and we find that weak acids are less than 5% ionized. We can look at the relationship between Ka and Kb, and we find that by multiplying Kb and Ka and Kb, we get Kw. Next, we're going to work on some problems and use the knowledge we have learned and apply it to different situations. Okay, so for the first problem, we have a 0.1 molar solution of HCNO was found to be 0.02% dissociated. Calculate the acid ionization constant Ka for this acid. This is a little bit different of a problem, but it's going to line up for an example that we're going to do later. So, first thing we're going to look at is that we know the first problem that we're going to look at says a 0.1 molar solution of HCNO was found to be 0.02% dissociated. Calculate the acid ionization constant Ka for this acid. This problem is a little bit different from ones that we have previously done, but we're going to follow roughly the same rules. The first thing we're going to do is write the equation. So we have HCNO, an acid, plus H2O gives us CNO minus plus H3O plus. Remember, to get these, we know that HCNO is working as an acid, so it's losing a proton, and H2O is working as a base, so it's gaining a proton. Next thing we're going to do is write the expression. Excluding water, of course, because it's a pure liquid. Now, we know that we have 0.02% dissociated, which equals to 0.02. And we know that this is the only thing that is part dissociated. So we're going to divide that by 100. And we know that the molarity for this is going to be 0.1. So we're going to just multiply it. This gives us what equals 2 times 10 to the negative fifth. This is what we're going to use as our concentration for CNO minus and H3O plus. So we're going to rewrite that expression now. We have X times X. So we're just going to write it as 2 times 10 to the negative fifth squared divided by our initial 0.1. Usually we just leave it at 0.1, But since we already know what x is, we can go ahead and put that in. So we're just going to have 0.1 minus 2 times 10 to the negative fifth. By solving this, we're going to get 4.0 times 10 to the negative ninth. And that is going to be our value for Ka. The next problem we're going to do says a solution of 0.1 molar hydrozoic acid was found to have a pH of 3. Determine the acid ionization constant, Ka, for this acid. This is really similar to a problem that we did above, but we're going to follow the same rules yet again. First, we write our equation. HN3 plus H2O gives us, and we know that this is working as an acid because it says Ka, so it's going to lose a proton, leaving us with N3 minus plus H3O plus. Next, we're going to go ahead and write our expression. N3 minus H3O plus over HN3. Okay. So we can go ahead and write our ice chart. So we have 0.1 of hydrozoic acid. Then we have N3 minus and H3O plus. 0, 0. Stoichiometry is 1 to 1. Minus x plus x plus x. We are left with x, x, and 0.1 minus x. Now, we know that the pH is equal to 3. So how do we determine the concentration of this? We know that the concentration of H3O plus is equal to 10 to the negative pH. So if we just replace these numbers, we know that 10 to the negative third is equal to x. We're going to go ahead and say that x is also equal to 1 times 10 to the negative third. Now, what we're going to do is input this number into our new equation. So we have 1 times 10 to the negative 3 squared over 0.1 minus 1 times 10 to the negative 3. And by solving this with a calculator, we find that our Ka value is 1.01 times 10 to the negative fifth. Next, we're going to look at hypobromous acid, HBRO. It is a weak acid with a Ka value of 2.0 times 10 to the negative ninth. What we're trying to do is calculate the pH of a 1 molar solution of this acid. So again, we're going to first write out the equation. we know that HBRO is working as an acid because it asks for Ka, meaning it's going to lose a proton, leaving us with BRO minus plus H3O plus. Okay. We're going to go ahead and write the expression for Ka, which is going to be BRO minus H3O plus over HBRO. And we know that this expression is equal to our Ka, which is 2.0 times 10 to the negative ninth. What it asks is to calculate the pH. So we want to find the concentration of the H3O plus. To do so, we write our ice chart. HBRO, BRO minus, and then our H3O plus. Okay. So we know that we start off with a 1 molar solution of this acid. We don't start off with any of the products. So what we're going to find is that for 1 mole, we're losing, for 1 mole, we're gaining, and another mole, we're gaining. So by combining these, we find that 1 minus x plus x plus x. Now we rewrite our expression with these values. So we're just going to have x squared at the top over 1 minus x equals our Ka, which is 2.0 times 10 to the negative ninth. For this, we are going to be solving for x. So to avoid quadratic problems, we're just going to exclude this x. So in reality, our problem is going to be x squared divided by 1 equals 2.0 times 10 to the negative ninth. To solve this, all we need to do is multiply 2.0 times 10 to the negative ninth by 1, which is the same thing, and then find the square root of that. So what we do is find the square root of 2.0 times 10 to the negative ninth. And that is going to give us 4.47 times 10 to the negative fifth. This is the concentration of H3O plus and also the concentration of BRO minus. But what the problem is asking you for is calculating the pH. To find the pH, all we have to do is find the negative log of the H3O plus, which we already know is 4.47 times 10 to the negative fifth. So if we just do the negative log of this number, we find that the pH of this acid in this situation is 4.35, roughly. Question 4 asks, determine the acetate ion concentration, the hydronium ion concentration, and the pH of an aqueous solution, which is 0.2 molar in acetic acid. So, first thing we do, as in almost every single problem, is write the equation. So we're looking at acetic acid, which is HC2, H3, O2, plus water, gives us, and since this is working as an acid, it's going to lose a proton, giving us C2H3, O2 minus, plus H3O plus. Next, we're going to write our expression, which is going to be C2H3O2 minus times H3O plus over the concentration of acetic acid, HC2, H3, O2. And we know already the value of Ka, which is 1.7 times 10 to the negative fifth. Next, we're going to go ahead and formulate our ice table. First, we're going to have HC2, H3O2. Then we're going to have C2, H3O2 minus, and then H3O plus. The problem gives us our starting initial in acetic acid, which is 0.2 molar. And we don't have any yet of the products, so they're both going to be 0. From the equation, we can tell that stoichiometry is 1 to 1. 1 molar of acetic acid gives us 1 molar of C2H2O2 minus, sorry, H3O2 minus, and 1 molar of the H3O plus. So we're going to find that our change is minus X plus X plus X. By combining, we can find our equilibrium. So for the acetic acid, it's going to be 0.2 minus X, X, and then X. We're going to go and input these values into our expression to get X squared over 0.2 minus X. Remember to avoid the quadratic problems. Just going to exclude this X. And we're going to equal that to the Ka, which is 1.7 times 10 to the negative fifth. We're going to solve for X. And to do that, we multiply 1.7 times 10 to the negative fifth by 0.2, which gives us 3.4 times 10 to the negative 6. And we just find the square root of that, which is going to give us 1.84 times 10 to the negative 3. Now, if we look back at the problem, what the problem is asking us for is the acetate ion concentration, the hydronium ion concentration, and then the pH. We know that the hydronium ion concentration is going to be this number, because we know that the stoichiometry is 1 to 1. So X is going to equal 1.84 times 10 to the negative 3. Since it's 1 to 1, that means our acetate ion concentration is also going to be 1.84 times 10 to the negative 3. So let's go ahead and write those down. So C2, H3, O2 minus, maybe? Yes. Both of these, since they're both equal to X, are going to be 1.84 times 10 to the negative 3, 1.84 times 10 to the negative 3. Now, it also asked for pH. We know that pH is equal to the negative log of the hydronium concentration. So by inputting this number into this equation, we know that the pH is going to equal 2.73. The fifth problem asks, determine the percent dissociation of the weak acid HF from solutions which have the following initial concentrations: 1 molar, 0.01 molar, 0.001 molar, and 0.0001 molar. What do you observe about the extent to which an acid dissociates as its initial concentration is varied? Keep in mind that the Ka of HF is 6.8 times 10 to the negative fourth. You know the drill by now. First thing we're going to do is write the equation. HF plus H2O gives us our acid, loses a proton, F minus plus H3O plus. We also write our expression, F minus times H3O plus over concentration of HF equals 6.8 times 10 to the negative fourth. Now, what varies in this problem are the initial concentrations of HF. So to save space and time, I'm not really going to write out each ice chart table. If you really want to for practice, feel free and do that. But I'm just gonna go ahead and write the different equations. So we know that because of the stoichiometry, it's going to be 1 to 1. Oh no, oh there we go. It's going to be 1 to 1. So most of the time it's going to be x squared. And then usually it would be minus x, but instead we're going to keep it as the first one is being 1 molar equal to 6.8 times 10 to the negative fourth. Then we have x squared over the second, which is going to be 0.01, also equal to 6.8 times 10 to the negative fourth. And we have our third, x squared over 0.001 molar equal to 6.8 times 10 to the negative fourth. And finally, all the way over here, we're going to have our x squared over 3 zeros is 0, 0, 0, 1 molar equal to 6.8 times 10 to the negative fourth. I'm also not going to solve each and every one by hand. I'm just going to tell you what they equal, but I'm going to tell you how to do it. Equals. So to solve this, all you have to do is multiply 6.8 times 10 to the negative fourth times 1. And then you find the square root of that number, which is going to be, what is that number going to be? It's going to be 2.6 times 10 to the negative 2. That is going to be equal to x. Okay. So to solve this, we do 6.8 times 10 to the negative fourth times 0.01. And then we find the square root of that number, which is going to give us 2.6 times 10 to the negative third. Similarly, multiply 6.8 times 10 to the negative fourth by 0.001 and find the square root of that number, which gives us 8.25 times 10 to the negative fourth. And this last one is going to be 6.8 times 10 to the negative fourth times 0.0001. Find the square root, which gives us 2.61 times 10 to the negative fourth. Now, we are not done because what it asks is finding the percent dissociation. What we've found so far is the concentration of F minus and also the concentration of H3O plus for each of these situations. To find the percent dissociation, recall that we're going to divide our concentration by the total in the solution already. So in this case, we're going to divide this number by 1. In the second case, we're going to divide this number by 0.01. In the third, by 0.001. And in the fourth, by 0.0001. Doing these problems, we get 2.6% dissociation by multiplying it by 100, then a 26% dissociation by multiplying by 100, a roughly 82% by multiplying by 100, and finally a 261% by multiplying by 100. We're going to notice as the initial concentration decreases, the percent dissociation increases. So the less in concentration, the more percent dissociated. We're going to skip number 6 because we need appendix 5. And let me see if I actually have it. I think I even skipped on here. Oh, I have it. So 6 is going to be so NO2 minus is a weak base. So we're going to have KB. So we're going to add NO2 minus. And that is going to be associated with our KB. Then we know that our conjugate acid for KB is going to be NHNO minus. And we know that this from appendix 5 is going to equal 4.5 times 10 to the negative fourth. And we know that also from appendix 5 that Kw for this is going to equal 1.0 times 10 to the negative 14th at room temperature usually. So what we want to find is Kb. But we know that the relationship between Kb and Ka is that when multiplied together, we get Kw. So to find Kb, all we need to do is divide Kw by Ka. This is going to look like 1.0 times 10 to the negative 14th divided by 4.5 times 10 to the negative 4th, which gives us our Kb, which is going to be equal to 2.2 times 10 to the negative 11th. Number 7 asks, determine the pH of a solution which is 0.12 molar in NaO2. Use the equilibrium constant value Kb obtained in problem 6. So this one is a little bit different from what we've been doing because NaO2 does not act as a base or an acid. So we're going to go ahead and write it out. So NaNO2 gives us Na plus 2 plus NO2 minus. So using these now, we can have one, the NO minus, work as a base. So our new equation is going to be NO2 minus plus H2O gives us HNO2 plus OH negative. Now we can continue with what we usually do and create our expression, which is going to be HNO2 times OH negative over NO2. If I go ahead and writing our ice chart, we can find that we have a beginner molarity of 0.12, 0 of HNO2, and 0 of OH negative. I'll just go ahead and write these since I forgot. The stoichiometry, we can find that for 1 mole of NO2, we get 1 mole of HNO2, and then 1 mole of OH minus. So by combining these, we find that equilibrium is 0.12 minus X, and then X and X. So we go ahead and input these back into our expression. So it's going to be X squared over 0.12 minus X. I'm going to exclude the X to avoid doing quadratic problems and equal it to the Kb obtained in problem 6, which is going to be 2.2 times 10 to the negative 11th. By solving for X, we find that X equals 1.62 times 10 to the negative 6. We found that by multiplying 2.2 times 10 to the negative 11th by 0.12 and then finding the square root. Now, what it asks for is the pH. So what we have is a concentration of OH negative. So we can use the concentration of OH negative to find the POH. So negative log of this number, 1.62 times 10 to the negative 6, gives us, let's see, negative log of 1.62 times 10 to the negative 6. That gives us the number 5.79. Now, notice how this is our POH, but the question asks for pH. Recall that POH plus pH equals 14. So what we're going to do is subtract 5.79 from 14 to get the answer that pH is equal to 8.21. We're going to go ahead and skip number 8 and move on to number 9. Number 9 says calculate the pH for a 15 molar solution of NH3. See Appendix 5 for KB. So, just like the previous problems, first thing we're going to do is write out the equation. So, NH3 is working as our base plus H2O working as our acid. Since it's working as a base, it's going to work as a proton acceptor. So it's going to turn into NH4 plus, and the H2O is going to give off a proton, becoming OH negative. Next one we're going to do is write our expression, which is going to be NH4 plus times OH negative over NH3. Next, write our ice chart table. Now we know that we have an initial of 15 molar and 0 for our products. So we know based on the equation that for 1 mole of NH3, we get 1 mole of NH4 plus and 1 mole of OH negative. Minus X plus X plus X. Combining to get equilibrium, we get 15 minus X, X, and X. So now we input that back into our expression, and we get X squared over 15. Usually the minus X would be included, but since we're solving for X, we're just going to go ahead and exclude it. And from Appendix 5, I already grabbed the KB, which is 1.8 times 10 to the negative 5th. We're going to go ahead and solve for X. To do so, you multiply 15 to 1.8 times 10 to the negative 5th, and you find the square root of that number. So X is going to go at 1.64 times 10 to the negative 2. Now, recall that pH plus pOH is equal to 14. We also know that to get pOH, we take the negative log of our OH negative concentration. We already found out that our OH negative concentration is equal to X, which is equal to 1.64 times 10 to the negative 2. So we just find the negative log, this number. This is going to give us 1.78. So this is going to be our pOH, but the problem is asking for the pH. So to get pH, all we have to do is subtract 1.78 from 14. And this is going to give us 1.22 for the pH. Oh, sorry. 12.22. So that concludes the last problem on the problem set. Um, Most of these problems are relatively similar. If you just follow the steps and remember the intricacies, then you're going to be mostly fine. I recommend remembering that Ka plus times Kb equals Kw, and also how to find percent ionization, which is the amount ionized divided by the total in solution times 100. So essentially, your X divided by your initial times 100. And that's about it for this. Next, we're going to review polyprotic acids and salt solutions, uh, which is going to build on this and focus on ice charts as well. So there you have it.